In this video, I'll introduce you to a fascinating quantum phenomenon. It emerges within extremely small scales and is known as the Casimir effect. But first, we need to understand two fundamental principles from quantum physics. The first principle is that of zero-point oscillations. Imagine a small weight on a spring, a classical setup known as a harmonic oscillator. At a classical level, this system is pretty easy to describe. If someone pushes the weight, it will begin to oscillate, with amplitude increasing as we impact more energy. By adjusting the force and its direction, we can freely change the oscillator amplitude or even bring it to a complete stop. But what if we shrink our oscillator down to an incredibly small scale, comparable to the size of atoms? Now, strange and counterintuitive quantum processes will begin to dominate. This will lead to two fundamental changes in our system. First, we can no longer adjust the energy of oscillations and thus their amplitude as we want to. We can only change them in tiny, discrete amounts known as quants. Yet, it's the second property that's more important to us. Now, no matter how hard we try, we can no longer bring the oscillations to a complete stop. No matter what methods we use, the weight will still undergo very small, but never entirely zero oscillations. This strange outcome follows from the uncertainty principle discovered by the great German physicist Heisenberg. The essence of this principle is that we cannot simultaneously know particle exact speed and its precise location. I won't go into deep details here, but I will only say that this is not due to our measurement techniques or impurity of our knowledge. This is the key principle of our universe itself. So, what happens if we try to stop the weight? Then we will know its precise location, where the spring is relaxed, and its speed, which will be zero. Therefore, this is impossible. These tiny oscillations are known as zero-point oscillations, or also they are called quantum fluctuations. The second principle is known as wave-particle duality. Let's look at an important example: electromagnetic waves. We encounter them every day. Examples include heat radiation, microwave radiation, radio waves, and most importantly, the visible light. From the definition, it's clear that we are dealing with oscillations of special form of matter, called electromagnetic field. From our everyday experience, it seems that a wave cannot be a particle. All waves that we know consist of ordered motion of particles, like waves on the water or oscillations of a stream. Both water and stream consist of particles, which actually performs the oscillations. But in quantum world, these things, like particles and waves, they do not contradict each other. On the contrary, they complement each other. At quantum level, quantum objects can perform both properties of waves and properties of particles. This dual nature of quantum objects are called wave-particle duality. Now, let's ask what will happen if we combine these two principles. On one hand, we have a field that fills all of space with oscillations that exhibit particle-like properties. On the other hand, we know that these particles can never remain perfectly still, the same as the oscillator in the beginning of this video. As a result, all of space is filled with numerous oscillations with different frequencies and almost zero amplitudes, while corresponding particles constantly emerge and vanish. These are called virtual particles as they cannot be captured by detectors. Yet that doesn't mean that they play an insignificant role in nature or do not interact with real particles at all. On the contrary, these particles give rise to numerous effects. One of the most striking of this phenomenon was discovered in the mid-20th century by the Dutch scientist Henrik Casimir. He based his theoretical discovery on two principles that we just discussed. Let's describe the essence of this effect. What do we have at this point? A space that is entirely filled with quantum fluctuations of electromagnetic field, essentially a bunch of electromagnetic waves. Now let's introduce a metal plate into this space. An important property of conductive metal is its ability to shield against electromagnetic waves, meaning they cannot penetrate inside it. You can easily check it yourself. If you warp your mobile phone in tin foil, it will lose signal. This is also the reason why some individuals made themselves foil heads in order to protect from aliens or something like this. So, the presence of a metal plate will limit possible oscillations of electromagnetic field only to those configurations where the field strength is zero on the surface of the metal. Now, let's place a second identical plate parallel to the first one, at a distance much smaller than the size of the plates. The result is that the waves outside the two plates are less restricted than those between the plates, as shown in this animation. Only waves that go to zero at both plates can fit between them, while those outside only need to vanish on one plate. And as we recall, these oscillations can be seen not just as waves, but as virtual particles, which interact with the metal plates and exert pressure on them. With a single plate, the pressure on both sides would be equal, but with two plates, the pressure outside is greater than the inside. In a way, the number of virtual particles outside the plates is greater than between them, creating a force that draws the two plates together. Let's emphasize the main points once more. This force isn't due to any real particles or some forces between the plates themselves. The space around and between the plates are as empty as it possibly can be. Yet, the force that drives the plates together arises from the intrinsic properties of the space itself. Vacuum is not just an empty space, as we taught in school, but it's a complex medium that can be in different states and influence the objects that are immersed within it. The next important question to ask is how strong this force, and can we observe it experimentally? The Casimir force between two plates depends on the area of the plates and the distance between them. On scales familiar to us, this force is extremely weak. For example, if the plates are spaced 1 centimeter apart, the area would need to be comparable to that of Australia for the Casimir force to equal the weight of a dandelion seed. However, as the area and distance between the plates change, the force does not scale evenly. Doubling the area doubles the Casimir force, but halving the distance increases the attractive force 16-fold. This means that as the distance decreases, these forces play an increasingly significant role. At distances around a millionth of a millimeter, these forces can even dominate, making their observation entirely feasible. Various measurements have been conducted in the second part of 20th century, following Casimir's theoretical discovery, and all of them have confirmed the existence of this effect. It was mentioning that we can study Casimir force not only between two parallel plates, but also between various configurations. For instance, Casimir force have been studied for a plane and a sphere, two spheres, and so on, including non-metallic objects. In almost all cases, the Casimir force is attractive. However, we can show examples at which these forces will be repulsive. A clear example of this is a small cylinder positioned above a plate with a hole, with the cylinder aligned directly over the hole's axis. If the cylinder is close enough to the hole, additional quantum fluctuations within the hole begin to push the cylinder away from the plate. Unfortunately, stable levitation cannot be achieved in this way, primarily due to the instability of the system. Any disturbances along the plate's surface will disrupt the balance. Despite all of these amazing properties, the Casimir effect has yet to find practical application in technology. There has been some speculation about using the Casimir force to create ultra-sensitive sensors, devices for heat transfer at the nanoscale, and even in quantum computing. However, none of these ideas have yet reached widespread use. Moreover, this effect can actually introduce additional challenges in the development of small-scale chips, where it must be taken into account. So, from this video you've learned that the vacuum itself is not simply an empty space, but rather a constantly changing ocean of virtual particles. And one of the most striking manifestations of this ocean is the Casimir effect.
If you enjoyed this video, please give it a like, subscribe to the channel or leave a comment. See you next time.